Hello dear friends, welcome to the lecture of integral transforms. In integral transforms, we are going to study two important integral transforms. The first is Laplace transform and the second one is Fourier transform. So in this lecture, we shall study Laplace transform. Then after studying Laplace transform, we will study inverse Laplace transform and then the applications of Laplace transform to solve differential equations. The Laplace transform, Fourier transform or integral transforms are useful to solve differential equations. Before defining Laplace transform, we shall see some properties of function which are I have written here, piecewise continuity and function of exponential order, function of class A, because these properties are the requirement for existence of Laplace transform. If a function has these special types of properties, then the Laplace transform exists. And therefore, before the definition of Laplace transform, we shall see the meaning of these type of functions. And the first one is piecewise or sectional continuity of a function. The meaning is simple. A function f of x is called piecewise continuous or sectionally continuous in an interval a comma b, closed interval a comma b, if it is continuous in every subinterval a1 comma b1 of ab and has finite left and right hand limits. So that is the meaning of sectionally continuous or piecewise continuous. So that is suppose this is the interval ab and the function need not to be continuous at every point from A to B. There are infinitely many points, but it must be continuous piecewise. That means if the interval A to B is divided in parts or into pieces, so that is say A1, B1, etc., A2, B2 and so on. So the interval is divided in parts and the function must be continuous in each subinterval a1, b1, a2, b2, etc. And that is the meaning. It is continuous in every subinterval a1, b1 of ab and has finite left hand limit and right hand limit. So that is the condition first we should have for existence of Laplace transform. The function must be piecewise continuous. If it is continuous in entire interval, then it becomes piecewise continuous obviously, but at least it must be continuous in every subinterval of AB. Now the second condition is function of exponential order. Now what is the meaning of function of exponential order? That is defined here. A function f of x is said to be of exponential order a. A is a number here, a real number, as x tends to infinity if limit x tends to infinity e power negative ax, e power minus ax into f of x, if this limit is a finite quantity or the limit is finite, then we say f of x is of exponential order. So why it is said to be exponential order? Because that function f of x is multiplied by this exponential function e power minus ax, and then the limit is x tends to infinity. If this becomes a finite quantity, then the function is said to be of exponential order. Now piecewise continuity we have seen, so I shall rub this part. And function of exponential order we will see. If the same thing is written like this using the definition of limit. When this limit is finite quantity, that is if given a positive integer n, capital N, there exists a real number capital M greater than 0 such that this absolute value of this is less than that real number m for x greater than or equal to n. So that is the meaning. Finite quantity means this finite quantity means it must be less than a certain number m, and this happens when x becomes greater than or equal to capital N, means x tends to infinity. So after some number, positive number n, maybe 100, 1000, etc., For after that x is greater than that number or greater than or equal to that number, this value of this absolute value of this product is less than a number m, real number m. That means this quantity is finite. That is the meaning written in other words, in inequality form. And if this absolute value is less than m for all x greater than or equal to m, sufficiently large x, or this may be written as, see, this is product of the absolute value, and therefore this term can be shifted on the other side, it becomes e power ax, or absolute value of f of x is less than, strictly less than e power ax into m for x greater than or equal to n. That is the meaning of function of exponential order. Now we shall see, for example, fx I shall take is equal to, simple example, x square is of exponential order. Exponential order a, or simply it is called of exponential order. How to show this? Since we have by this definition, limit x tends to infinity e power minus ax into fx is x square. So this can be written as limit x tends to infinity x square divided by e power ax. Negative power becomes positive at the denominator. And now if you put x tends to infinity here, assuming that a is positive, x square is again infinity, square is infinity, and this is also e power infinity is infinity. So this is of infinity by infinity form, and we can use the L'Hopital rule for this limit, to evaluate this limit. That means we should take the derivatives at numerator and denominator, and this can be written as limit x tends to infinity, and we have to use the rule two times, because one's derivative will be 2x divided by a into e power ax. Again x remains at numerator, means it is in this form, infinity divided by infinity. So taking the derivative two times or twice, the numerator becomes 2. First derivative is 2x and second derivative is 2, and the second derivative of this is a square e power ax. And certainly when x becomes infinity, the denominator becomes infinite, numerator is finite, and therefore the quantity becomes this is written by L'Hopital rule. Applying the rule twice, and therefore this is 0. 0 is a finite quantity. 1 over infinity becomes 0, and thus this is an example of function of exponential order. So that is the meaning, this limit must be finite, or in other words, this can be written as absolute value of f of x is less than, strictly less than e power ax into m, where m is a real number. There must exist a real number such that the absolute value is less than this one. Thus we have seen two types of properties of a function. Piecewise continuous means the interval is divided in parts and the function must be continuous in each subinterval. And second is function of exponential order, which has this condition or this one. And then we have function of class A, capital A. So a function of f of t, it may denote, we will now denote the function as function of t, and f of t is said to be of class A if it has these earlier two properties. That means it is piecewise continuous if it is piecewise continuous over every finite interval in the range, positive range of t greater than or equal to 0, or non-negative range. And second is f of t is of exponential order. If these two properties are satisfied, then we say the function is of class A. So that we have to remember. Function of class A means of two properties, having two properties. First is piecewise continuous and second is exponential order as t tends to infinity. Instead of x, we are using t. Now with this function of class A, we should only understand the meaning of this function of class A, which has two properties. Now we will see what is meaning of integral transforms. it is an improper integral of this form. Integral minus infinity to infinity k, it is a function of two variables s and t, k s comma t into f of t dt. That means a function integral transform of this function f of t we have written. That f of t is multiplied by this another function k of s comma t, function of s and t, and then it is integrated between minus infinity to infinity with respect to t. Then that becomes integral transform. That means it is a transformation or change of function using the integral, and not only the integral, but it is first multiplied by this function k of s comma t, and then it is integrated in the range minus infinity to infinity. Why the integral is called improper? If the range is infinite, range of integration is infinite, then the integral is improper, or the function is infinite, then also we say the integral is improper, and therefore this improper integral is known as integral transform. Why the word these two words are used? Integral, with the help of integration the function is transformed. And if we say this is the integral transform, the condition is if it is convergent. The integral must be convergent, means the integral must be finite quantity. It is denoted by t of f of t. T is the notation used for transform, in transform of f of t, or another notation is small f of s. Here s is the parameter we have, and the function k of st, this function is called the kernel of the transform, kernel of the integral transform, and here s is a parameter. Now this is the general integral transform, and using this form of integral transform, different transforms are integral transform, different types of integral transforms are defined. So one is Laplace transform, another is Fourier transform, Henkel transform, Mellin transform, etc. In that case, this kernel is different. So for different integral transform, the kernel is different. And now we shall define the Laplace transform. Mainly we are studying Laplace and Fourier transforms. These are main transforms, and we are going to study these two transforms. So if we have this k as, say, k st as e power negative st when t is greater than or equal to 0, and 0 when t is less than 0. That means the function is defined, this kernel is defined for non-negative values only. When t is negative, this value is 0, and therefore this range becomes 0 to infinity, because for infinity, minus infinity to 0, the function is 0, and therefore it does not exist, and this integral transform becomes 0 to infinity, and k is e power negative st, and f of t remains the same, dt. Then this integral is known as Laplace transform. So this is the Laplace integral transform. That is the definition for Laplace integral transform. If f of t is a function defined for t greater than or equal to 0, then integral 0 to infinity e power minus st f of t dt is called the Laplace transform. Of f of t, capital F of t. This is a general definition of integral transform, and especially for Laplace transform, k is taken in this form. For Fourier transform, we have k as, for sine transform we have it is sine st. For cosine transform we have k st as cos st, and for infinite Fourier transform we have e to the power minus ist. This will we will study in the chapter of Fourier transform. But for Laplace transform, k is taken as e power minus st and is called the Laplace transform of f of t, capital F of t. And is denoted by L stands for Laplace, L of f of t, or another notation is f of s. There are different notations to denote Laplace transform. So it may also be denoted by fs, or it may be denoted by f bar s, or it may be denoted by f tilde s, or in place of s p may also be used. So these are the different notations for Laplace transform. Now here s is the parameter we have. Thus the definition we should have to remember as this one. Thus L of f of t may also be written as f of s and is equal to integral 0 to infinity e power minus st into f of t dt. This is the definition of Laplace transform. And so it is easy to remember. It is integral, range is 0 to infinity. For general it is minus infinity to infinity, but for Laplace transform negative value function is not defined. It is defined for t greater than or equal to 0. So range becomes 0 to infinity. The kernel k value is e power minus st into f of t dt. So that is the Laplace transform. And sometimes it may be denoted by f of p also. In that case it can also be denoted by, or we may say sometimes we write this as L of f of t is equal to fp. In place of, this is a parameter s, in place of s sometimes p may also be written, and in that case the change will be, it is integral 0 to infinity e power minus pt. In place of s we are writing p and t remains the same. So this is the another notation for Laplace transform. Now we will state and prove a theorem of existence of Laplace transform. What is the condition whether all functions have the Laplace transform, say is the Laplace transform. So if then if it exists, we can add here also, then this integral, if it is finite or convergent, then it is called the Laplace transform of f of t. So the condition must be that this integral must be convergent or finite, then it is the Laplace transform. Now we will state the condition for existence, that is as a theorem 1, first theorem, existence of Laplace transform. And the condition is the function must be of class A. That's why we have defined function of class A. If f of t, capital F of t, is a function of class A, then the Laplace transform of f of t exists. So this is the condition for existence. Function is so this condition is sufficient but not necessary. Some functions which are not of class A, for that also some functions, not all, the Laplace transform exists. But if function is of class A, then there is certainly the Laplace transform exists. So we shall prove it. Given, let f of t be a function of class A. Then f of t is, see these two conditions. First, f of t is first piecewise continuous or sectionally continuous, over every finite interval. For t greater than or equal to 0. And second, f of t is of exponential order. F of t is of exponential order as t tends to infinity. So these are the conditions. Now we have to show the Laplace transform exists. Means what? We have to show that this L of f of t, this exists. So we have to show that L of f of t, which is by definition of Laplace transform, this is integral 0 to infinity e power minus st f of t dt exists and for all s greater than a. Exponential function of class A we shall assume, and therefore we will assume that s is greater than a. Now suppose t is a finite number. Let now for any t naught greater than or equal to 0, we have that is in this range 0 to infinity. Consider any number t naught. That means we are considering the range of integration is 0 to infinity for this, and we will assume t naught is somewhere here, that is greater than or equal to 0, any value in the interval 0 to infinity. So then we have this integral L of f of t, the Laplace transform is integral 0 to infinity, that we should split in two parts, 0 to t naught by property of definite integral e power minus st f of t dt plus t naught to infinity, 0 to t and then t naught to infinity. The integral is split in two parts, and the second is this one. Now see, we will assume this as this as 1 and this as 2. Both are actually the same, but now you see t naught is for any t naught greater than 0 finite. We will assume t naught as finite. So any finite value, any finite t naught greater than or equal to 0, we can write the integral in this form. Now this is finite, means the interval is 0 to t naught, which is finite, and the function is, we have by the first condition, piecewise continuous, means the function is 0 to t continuous in the interval 0 to t naught, and therefore because the function is continuous, this integral is convergent or finite. Since f of t is piecewise continuous or is continuous in the interval zero to t naught, the first integral, the integral 0 to t naught e power negative st f of t dt is finite and exists, is finite and hence exist, hence it exists. When we say a quantity exists, the quantity is finite or it is fixed. Then because this t naught is finite, we have assumed, and the interval becomes finite, and therefore the function is continuous by this condition. In the total interval is 0 to infinity, and that is a part subinterval of 0 to infinity, and the function is continuous in that subinterval, and because of continuity the integral is finite. So therefore this integral is finite. Now we have to show the whole integral is finite. If this also is finite, then both these quantity are of finite, means the integral, Laplace integral is finite. So that we have to show. So further we have to show that the second integral is also finite. Now we shall show that the second integral on RHS of 2. Second integral on RHS of 2 is also finite. Now for that purpose we shall use this second condition, that is f of t is of exponential order as t tends to infinity. Since f of t is of exponential order A, we will say, as t tends to infinity. So we have, by definition of exponential order, function of exponential order. So we have written it earlier. So what that implies, we have there exist, we have for any positive integer t naught, t naught, there exists a real number capital M. See, this is the definition of function of exponential order. There exists a real number capital M such that absolute value of f of t is less than, strictly less than e power at into f of t for all t greater than or equal to t naught. That t naught we have considered. See, for any positive number t naught is, we have considered this t naught, t is greater than or equal to t naught, means it is in the interval t naught to infinity. In that interval the absolute value of the function f of t is less than e power at into not f of t but m. So we have the integer m. So this is the definition of a function of exponential order that we have written earlier. So this is the case, and we will see this result as 3. Now we will have this absolute value of this integral. Next, this is the integral t naught to infinity. We will take its absolute value. Integral t naught to infinity e power minus st f of t dt. This is less than or equal to, we are using the property of again the property of definite integral, is less than or equal to integral t naught to infinity e power minus st mod of f of t dt. See, this is the result we have, that is absolute value of integral f of x dx is less than or equal to integral of absolute value of f of x dx. So this is the property, and according to that property we have written this. So but now you see this mod of f of t is less than e power at into m, and therefore we will write that as, or this is this result is used there, and I will continue here as this is strictly less than integral t naught to infinity e power minus st, and this mod of f of t is less than e power at into m dt. M is the real number, and now this can be written as, this is actually less than, now further it can be written equal to, so that is equal to, or this quantity is equal to, this quantity is equal to integral t naught to infinity e power, or that m is a real number, and therefore that can be written outside the integral. So this is m, and what remains inside integral is e power minus, I shall take minus sign common, and s minus a into t dt. You see, negative sign is taken, s minus a, minus of minus becomes plus a, at, e power at, e power minus st. And what is integration of this? This is equal to m, integration of this we know, e power minus s minus a times t divided by the coefficient of t, that is minus s minus a, and limits are t naught to infinity. S is, we are having s is greater than a, and therefore this will be, so I shall write here, this will be equal to m, and see the upper limit, it is e power negative infinity divided by this quantity, and minus of minus, lower limit is t naught, so minus, and this minus becomes plus, and we have that as e power negative infinity is tending towards 0. E power negative infinity is 1 over e power infinity, and that tends to 0. So therefore this is quantity 0, and then that minus of minus becomes plus, and what is the remaining is e power minus s minus a into t naught, the lower limit is t naught, divided by s minus a. So this quantity remains, and further that is finally equal to m into this expression, m into this expression. And but you see, what is the relation between this integral and the last expression? That is strictly less than. So here I have written equal to sign, but that equal to sign is for this expression, you remember, and but the relation between the left side and the right side quantity is strictly less than, or thus we have absolute value of the integral t naught to infinity e power minus st into f of t dt is strictly less than m into e power minus s minus a into t naught divided by s minus a for all s greater than a. This is the symbol for all. And what this suggests, you see, this is the left side I have written, and the relation between that left side and final quantity is less than. So this integral's absolute value is strictly less than this expression. Now what about the value of this expression? This can be made smaller and smaller by taking t naught large and large, or sufficiently large. So because when this is the large quantity, e power negative of that large quantity. So if I take t naught as say 100, and this s minus a will be some finite quantity as 2, then it becomes 200, e power negative 200, and this is 1 over e power 200, and the quantity is smaller. This is smaller between 0 and 1, and if we increase this value, then this quantity will approach towards 0. That means this right side can be made small and small by taking t naught sufficiently large. So because we have already written here e power negative infinity is tending towards 0. So therefore if this negative power increases with negative sign, then the quantity approaches towards 0. Means this is a smaller quantity, and smaller quantity means this is a finite, and thus this is what we have to show. This quantity or the second integral is finite. This first is already we have shown it is finite. So this is a finite quantity, and the second is also a finite, and therefore addition of two finite quantity will be finite, and that means the Laplace transform exists. It is a finite quantity, then it exists. So we can write here as the right side of this inequality can be made smaller by taking t naught sufficiently large. Hence, the RHS is finite. Therefore, this integral is finite. This quantity is finite. That means absolute value t naught to infinity e power minus st f of t dt is finite, and hence the second integral in the equation 2 is finite. Hence equation 2 the RHS of 2 is finite. And therefore RHS of 2 is finite means the Laplace transform is finite. Therefore L of f of t becomes finite, is finite, and hence exists, and hence it exists. So this proves the theorem. So this is the theorem which says gives the condition for existence. This proves the theorem. That means if the function is of class A having two properties, piecewise continuous and of exponential order, then the Laplace transform exists. So thus we have proved the existence theorem of Laplace transform. But we should note one condition as a remark, that one statement as a remark. The condition is in theorem 1 is sufficient but not necessary. Is sufficient but not necessary. So what is meaning of this? Without satisfying the condition, the Laplace transform may exist. So but the meaning is sufficient condition means if it is a function of class A, then certainly the Laplace transform exists. So for example, the function, if we say f of t is equal to t power n, is not of class A, but the Laplace transform exists. L of t power n exists. So this we shall actually obtain the Laplace transform in our further part. We will obtain the Laplace transform of this t raised to n. It is not a function of class A because see, if it can be written as t to the power minus n, and if n is say positive value, n is negative value, then we can write it as 1 over t to the power minus n. So this is not continuous at t is equal to 0. This function is not continuous at t is equal to 0. So for example, if you consider t raised to negative 3, then that can be written as t 1 over t cube. this function is not continuous at t is equal to 0, does not exist at t is equal to 0, and therefore it is not a function of class A, but till the Laplace transform exists. So that also we have to note. So thus we have proved the theorem on existence of Laplace transform. The remaining part is comparatively easy than this theoretical part. We will obtain standard functions Laplace transform, and then there are further simple rules we shall define. So remaining part we will continue in our next lecture. Thank you.